Hi, my name is Charles Dawson, and I'll be presenting our paper, Learning Safe Perception-Based Hybrid Control with Certificates, on behalf of myself and my co-authors, Bethany, Dylan, and Chuchu. When we talk about control systems, often our first thought is about state feedback controllers. In this setting, a control system receives information about the state of the robot, either directly measured or inferred using state estimation, and uses that information to make control decisions. This setting is relatively easy to model mathematically, and there are a lot of existing methods for control synthesis. In addition, if we're interested in making guarantees about safety or stability, we can do so using certificates like Lyapunov and barrier functions. However, when we want to move to robots that have more complicated sensor models, we often don't have access to the state feedback or a state estimate. Instead, the control system needs to make its decisions on the basis of observations in the form of, say, LiDAR data or depth images. This model of observation feedback control is needed to deal with rich sensor models that we often see in real-world applications. However, it is difficult to model, and it's also difficult to provide guarantees about things like safety and stability. In this work, we hope to develop a framework for building observation feedback controllers that allows us to make some guarantees about the safety and stability of the resulting perception feedback system. To do this, we consider a simplified setting where this ground robot receives perception data in the form of laser scans, shown in green, and range and bearing with respect to some goal point. The design objective here is for the robot to avoid obstacles without having a prior model of the environment, and to reach its goal without getting stuck. In addition, we want to do this while providing guarantees. First, that the robot avoids collision, which we do through the use of a control barrier function. Second, that the robot will eventually reach its goal through the use of a control Lyapunov function. And third, we use a hybrid controller to prove that the robot will avoid getting stuck or avoid entering deadlock. The architecture that we use is as follows. At a high level, we use a hybrid controller with a goal-seeking and exploratory mode to navigate through the environment. And we design the switching between these two modes to ensure that the robot will not get stuck and will continue to make progress towards its goal. At a low level, we use an approximate look-ahead model to predict observations one step into the future, and use these predictions in conjunction with an observation-based control barrier function, an observation-based control Lyapunov function, to make decisions about which control actions are safe and stable. We can see this control system in action in this environment, which the robot has never before encountered. At the top, we see the control barrier function, which measures how safe, i.e. negative, or how unsafe, positive, the robot is. The control barrier function hovers around 0, showing that the robot is exploring the boundary of this obstacle to navigate around it. The control Lyapunov function, bottom here, decreases as the robot gets closer to its goal. When the robot was exploring the boundary of the obstacle, it allows the control Lyapunov function to temporarily increase. But once it rounds this corner and re-enters the goal-seeking mode, it is able to decrease the Lyapunov function again as it gets closer and closer to its goal. We can also compare our approach with online planning and SLAM. The SLAM method initially constructs a map of its environment, allowing it to plan a more optimal path. However, when we introduce a new obstacle to the environment, the map is invalidated and the robot gets stuck. In contrast, our method is able to smoothly react to the newly added obstacle and continue navigating towards the goal. The SLAM method does eventually reconstruct its map and continue, but after being stuck for a considerable amount of time. I'm happy to take questions and go into more detail about our approach or refer you to our paper.